Name is Thibault Rousset. I will present the research I did in collaboration with Fujitsu Research. So the team with Taisei, Kakibuchi, Yusuke, Sasaki, and Yoshihide Nomura. The title of the research is Merging Language and Domain-Specific Models, the Impact on Technical Vocabulary Acquisition. And basically what we did is we explored cross-lingual knowledge transfer and specialized terminology comprehension in language models. So the introduction, so the base observation is that today LLMs are very powerful, but the one size fits all actually seldom works for when it comes to specialized fields. For example, medicine, law, engineering, or basically any field where specialized terminology is very important. And the problem is that general purpose LLMs that we use lack usually that deep domain-specific knowledge and comprehension, especially when it comes to technical jargon and terminology. And misunderstanding those technical terms in such domains can have significant consequences. We think of medicine, where not understanding that large terminology can lead to drastic misunderstanding and errors at the end for the user. And the current approaches are usually full retraining or fine-tuning, which is, as we all know, very costly and usually very data intensive. And integrating specific domain knowledge, especially when it comes to multilingual settings, but even in monolingual settings, without experiencing any kind of forgetting or catastrophic forgetting, remains an active challenge today. So in this paper, we decided to focus on investigating how could or whether could model merging be an effective solution for enhancing that technical vocabulary comprehension, and particularly in cross-lingual settings. So the core problem is how could we use model merging to integrate that technical vocabulary comprehension from one monolingual language model into an expert one, into a general purpose model of another language, and how to cross that language barrier effectively to achieve a model that is good basically at both language, or at least that becomes an expert in his language from from the model, the expert model, like transferring that knowledge. So 4 key questions. How could or does merging really improve domain-specific proficiency through the lens of technical terminology understanding? Is also the general language understanding, those general language linguistic capabilities preserved? How do different merging strategies compare when it comes to those particular tasks? And what are the challenges in cross-lingual knowledge transfer of specialized terminology? And the objective is to evaluate as comprehensively as possible how could standard model merging techniques could be a way to enhance domain-specific technical vocabulary acquisition while preserving our knowledge bases, retaining those core linguistic capabilities. So research has been done on such questions, or at least on related questions, especially on what we call LLM domain adaptation, how to adapt an LLM to a specific domain. Medical domains, law, engineering, those are kinds of domains where it's increasingly important to adapt our domain from a general purpose one. And model merging is one technique that has been researched on, that leads and that actually yields quite good potential. So model merging is basically, the core concept is to combine the strength of multiple models, usually a general one and a domain-specific one, and how to merge the knowledge bases and achieve a model that basically has those two knowledge bases that is good at what basically that has the same performance as both models. It's a cost-effective alternative to full retraining because model merging is actually quite easy when it comes to computation, even if there are still quite like a lot of challenges when it comes to model compatibility. We have quite strict requirements when it comes to what models we can use on what pre-trained model it comes from. Also knowledge interference, because we have two knowledge bases that could be interfering, that could lead also to problems when during merging, and computational efficiency. Even though it's quite cost effective, we still have a problem of computational efficiency. But it yields a lot of advantages over fine tuning because we don't need the data in settings where data is either expensive or we don't have access to it. It's a good alternative, and over continual learning because continual learning suffers from catastrophic forgetting in quite large magnitudes. So which is something model merging experiences, but on a lesser level. Other key concepts is cross-lingual knowledge transfer, how to leverage the knowledge from one language to improve performance in another. Crucial concepts for multilingual LLMs because we want to achieve multi-LLMs which are good in across a wide variety of languages and that keep a coherent knowledge base. We don't want to the models to contradict themselves in different languages. And the challenges are mainly language interference. We sometimes have language pairs that are quite different from each other, and that leads to quite to important challenges of language interference, and also language-specific biases and cultural nuances that have to be addressed. And in this paper, we addressed the gap and we focused on the intersection of both of those two concepts specifically for technical vocabulary. So our experiment, the core of our experiment is to merge an English medical domain expert language model with a Japanese general purpose language model. We focused on the medical domain because it's a quite good example of a domain where technical vocabulary is extremely important and is large. We have a large set of terms in the medical domain that usually are seldom encountered during pre-training for those language models. We have a lot of terms that are very technical and that could not be easily inferred from pure linguistic capabilities. We have to understand really deeply what those means and to learn them in order to be able to use them effectively in downstream tasks. And we chose English and Japanese because, as we said before, language interference is quite a important challenge, and we put ourselves in the worst case scenarios where we have two languages which are very far from each other. English and Japanese share little linguistic concepts. So we wanted to see how those merging techniques behave in that worst case scenario. The models we used are, for the Japanese general purpose, is Suzume, which is an 8 billion parameters fine-tuned version of Llama 3 Instruct. We use an Instruct version of Llama 3 because we wanted to be able to give the models quite specific instructions when it comes to the definition generation. I talk about it in a moment, and to be able to have control over the generation. And the English medical domain specific is contact doctor, also 8 billion parameters and also fine-tuned from Llama 3 structs. Very briefly, it's requirements. We have both both models that are fine-tuned from the same base model, because it's a requirement for the merging methods we use to have the same pre-trained model to ensure coherence and minimize the merging artifacts. So that we took that requirement in account and chose both models from the same pre-trained checkpoints. And emerging methods that we analyzed, so 6 of them, those 6 are in a subset of merging method that we call parameter-based. We did not analyze, for example, mixture of experts methods that could be considered merging methods. We decided to focus on those parameter-based, firstly for computational efficiency. Those are the methods that are computationally the less demanding. They are quite easy for computation, for computers to compute, and also to remain coherent and not introduce another layer of complexity. We wanted to be able to restrain the subset of categories to be able to see whether those particular merging methods could be able to handle technical vocabulary effectively. So what those 6 ones, the main differences are how to compute the merged weights, because parameter-based, to go very briefly over it, we basically take both model, the weights for both model, and we try to compute a formula or an average of those weights, and we have as an output a mathematical formula, mathematical equation that that relates the weights of the 2 models to the resulting one. The only difference is basically how to compute that, and also the 6th one is an evolutionary variant of one of the merging methods. So the methodology, I will go over the whole pipeline quite briefly to explain the experiment. So we first created the data set, the vocabulary data set. The source is the systematized nomenclature of medicine, which is called SNOMED. It's a quite huge corpus of medical nomenclature. We have publications, medical publications, medical reports. We have all those documents. The systematized nomenclature is extracted from it. We filter it to retain only the words with frequency 0, 1 in the brand corpus. This ensures that the words that we choose are technical and are not encountered in casual English or in modern everyday language, and also to ensure that it's seldom encountered in the pre-trained corpus, because we want our models to, we want to effectively see how our methods behave when it comes to words that are not encountered, that they don't know about, even though they were pre-trained on quite large corpuses. So yeah, it ensures that we have specialized rare technical terms. And we also focused on nouns and adjectives only. This comes from the fact that in English and Japanese, other part of speeches such as adverbs or verbs are handled quite differently. And we wanted to minimize the translation artifacts and decided to focus on nouns and adjectives, which are handled quite similarly in both languages. So we had, after pre-processing, a final data set of about 1,800 technical medical terms. And we translated them from English to Japanese using GPT-4o. And how did we evaluate our merge model on that vocabulary data set? The task was to generate the definitions of those medical terms. It's different English, and we have two parts, in English and Japanese parts. the English expert model defines the English terms in English. That provides the baseline definition because it's the expert model. It's supposed to understand quite good or quite well what those terms mean. And then for the Japanese models, so the Japanese general purpose and the merge models are asked for the Japanese translated terms definition in Japanese. And then we evaluate them, we judge those definitions using judge models, so GPT-4o as a primary evaluator and Gemini 1.5 Pro, and they score those definitions on a 0 to 10 accuracy scale. And those judges, LLMs, they receive the term in both English and Japanese, as well as the English baseline definition as reference. And then they are asked to judge the definition that is provided in Japanese. It's quite important that we choose GPT-4o as both the judge LLM and the translation LLM to be able to minimize also translation artifacts. We also evaluated on benchmarks. So the purpose is to assess both retained overall linguistic knowledge and acquired technical jargon proficiency, and also identify if there are any cross-lingual knowledge transfer mechanism. 3 benchmarks we used: JMate Bench, which is the cross-lingual knowledge transfer benchmark. A subset of tasks, quite 3 tasks. So it assesses the domain-specific expertise, so Japanese domain-specific expertise in Japanese. And then we have the base knowledge retention benchmarks, which are PubMed QA for the English medical knowledge, and the Japanese LLM leaderboard, which are the general language knowledge proficiency, Japanese language proficiency. We evaluated for most of those tasks in 0 shots, and some Japanese LLM leaderboard tasks were evaluated in few shots. So this graph gives an overview of the whole pipeline. We first prepare the dataset and translate it in Japanese. Then we have the definition generation in both Japanese and English separately. And then we go through evaluation using our judge models. So when it comes to the results, that's an overview of the definition evaluation scores given by the judge LLMs. So the key finding is that we have very minimal improvement actually, or a slight decline in for some models in defining the technical medical terms for the merged models. When we compare it to the base non-expert Japanese model, the base non-expert Japanese models has a quite average performance, what we would expect from a non-expert model, but we have minimal improvement even though we merged it with an expert model. The baseline English expert model, we also evaluated them to validate the coherence of our evaluation methods. Basically, is our judge model, is our baseline English model, does it give a good definition of it? We have near perfect score, which actually validates it. And the base Japanese model, I would say lower scores because non-experts. But the merge model, both in statistical metrics that we saw previously and in score distribution, very, very similar to the base Japanese model. One of the techniques, SLUP, showed a very slight improvement, but quite negligible when we compare it to the expert baseline. So that hints at that merging does not transfer, or at least does not significantly transfer, that ability to define specialized medical terms from the English model to the Japanese model. It hints at we actually have no we have a quite good metric that those transfer mechanisms do not happen on a technical jargon level. So those are the scores distributions. We can see that the baseline basically achieves near perfect scores, but all of the charts from C to H basically have quite similar distribution as B, which is the base Japanese model, sorry. And then when it comes to benchmark performance, we have here a overview of the benchmarks. We assessed the performance of all our models, so both baseline, so base models, and the merged ones. And here we see quite contrasting performance compared to the vocabulary task. We have good monolingual knowledge transfer, meaning inside one language. So we have good transfer of the English medical knowledge. Merged models performed quite well, sometimes outperforming baselines in some tasks, not by a noticeable amount, but at least it performed quite similarly. This suggests that knowledge from the English medical expert model was actually retained and effectively retained in the merged models. And for it's the same observation for general Japanese linguistic abilities. We have the merged model that showed variable but generally good results, indicating that we also have our general Japanese capabilities that were retained from the base general purpose LLM to our merged LLM, sometimes enhanced as part of QA, but not very noticeable. It's basically we have very similar performance. However, when it comes to the cross-lingual knowledge transfer, we have very poor performance. The JMIT bench, merged models generally failed to even surpass the base Japanese model. We have to keep in mind that the base Japanese model is not an expert one, so those performances are already quite poor, but the merged models actually fail even worse. They're actually even worse than the base non-expert model, meaning that we have poor cross-lingual knowledge transfer. We can even it even hints at a interference. We have an interference that actually lowers the performance on the JMIT bench. And we can connect both performance analysis and saying that the poor performance on JMIT bench aligns with the poor vocabulary acquisition, meaning that the inability to transfer that technical terminology across languages seems to be the reason why, or at least a bottleneck for higher level cross-lingual knowledge, domain knowledge transfer. So what do these results mean? Quite quickly, model merging has a lot of potential for monolingual knowledge transfer. So transferring medical domain or medical terminology knowledge from an English model to an English model, or Japanese model to an English model, Japanese model to a Japanese model. But when it comes to cross-lingual transfer, it fails quite drastically. And vocabulary is also quite an important bottleneck for those models that can explain why they are also the performance is quite low on higher level downstream tasks. We have also the merging complexity. Current merging methods could introduce complexities that impede the integration of specific terminology across different linguistic structures. What we saw just earlier, meaning that not only the performance are low, they're actually lower than the base models, meaning that we have something that even that worsens the knowledge of the model. And the evolutionary data is quite a good example of it. It performed quite poorly on both vocabulary acquisition and JMIT bench, so the cross-lingual knowledge transfer, reinforcing that link between vocabulary and downstream task performance. Yet it did quite well on PubMed QA, meaning that we have effective monolingual specialized knowledge retention. And as a conclusion, so model merging can be an effective method to facilitate monolingual knowledge transfer. However, cross-lingual knowledge transfer of technical vocabulary, but as a whole, cross-lingual knowledge transfer is a major challenge for current emerging techniques, as they do not significantly improve performance. And we have an important need for improved strategies that are optimized for that cross-lingual integration of specialized terminology if we want to achieve models that are that achieve that cross-lingual transfer. Our study do have its limitations. We relied on LLMs and judges, which are may not capture full human nuance, but also we have quite poor control over the evaluation method. Even though we can assess its coherence, we do not have control over the fine details of how does it compute or how does it relate thing. We focused only on Japanese English, which, as we said, is the worst case scenario. Maybe it behaves a bit better in closely related languages, and also the medical domain, which asks the question, is it generalizable? Is medical domain too hard a task for it? Maybe it behaves better on law, engineering, or other domains. We only limited ourselves to 6 merging methods, which is far from being a full overview of the ecosystem. And we also saw a very minimal impact of hyperparameter tuning. And though it suggests robustness, further optimization might help discovering hidden mechanisms. And as future research directions, refining existing emerging methods, exploring alternative strategies for cross-lingual specialized integration, investigating impact of different language pairs in different domains, and developing a more nuanced evaluation pipeline to assess the vocabulary acquisition. Thank you very much for your time and attention.